Hi, my name is Ernst Bekker, Product Specialist of Cyclones at Multotec Process Equipment. On this topic, we're going to look at the usage of dense media cyclones in the application of fines beneficiation. It's not a common application, but there's a trend that people are moving more and more into this direction. And as the topic indicates, are we there yet? Do we know exactly what to do? And I'm taking you through this presentation and we'll discuss some of the areas where we know what's going on and some areas where there might be still some work to be done. So we will be looking at the dense media cyclone basics very briefly, because dense media cyclones is a topic on its own, and this is not the purpose of this presentation. This is just a high-level overview. We're going to then look at why would one look at fines DMS. DMS being dense media separation. And then lastly, what points do we need to consider? What factors is there that we need to take into consideration? So starting off then with the dense media separation basics. Dense media separation is where we want to separate heavy material and light material by using then a liquid other than water. As the picture on the left hand shows, if you immerse rock in water, it settles to the bottom. However, if you introduce a medium like magnetite or ferrosilicon, it's possible to float the rock as shown on the right hand side. In this video, it is an illustration of how the cyclone operates. It's operating on a water only basis, but inside the cyclone you can see there's some yellow beads. And that's just illustrating the amount of time the particles spend inside the cyclone to do the separation. Time is of utmost importance to ensure optimum hydrocyclone performance. In dense media separation, there is a terminology, the partition curve. And what that is the following. The blue line on this graph illustrates perfect separation. And the density where there is no light material reporting then to the underflow is given as the cut density. The cut density is defined as the particle density that has a 50-50% chance of reporting either to the floats or overflow or to the sinks or the underflow. Unfortunately, dense media cyclones are not perfect separators. As illustrated in this animation, you get particles that's getting misplaced with sinks reporting to the overflow and light material reporting to the sinks. The objective, of course, is to have this S-curve as steep as possible, or to approach perfect separation as close as possible. In dense media cyclones, one of the factors that play a role is the particle size. There is a top size limitation to ensure there's no blockages taking place, and then there's a bottom size limitation to ensure that we always beneficiate the material as efficiently as possible. The focus of dense media cyclones, or fines dense media cyclones, is now focusing on this finer fraction which is normally not advisable to be treated in large diameter cyclones. A typical flow sheet of a dense media plant indicates or shows that the dense media cyclone always forms the heart of a process. On this cold flow sheet, you will see that the fine fraction is reporting to a water-based application, in this example where there's spirals and flotation. The fines dense media separation process is focusing on that territory. Moving on then to why fines dense media separation. What is the advantages, or why would one do that? The table that is presented on top of the slide is divided into a media-based section and a water-based section. And you will see that there is an EPM and an EPM divided by cut density. The lower the EPM value, the better the separation efficiency. If you look at the water-based applications, which is spirals, reflux classifiers or tetherbed separators, or TBS as they called, you will see that the EPM divided by SG50, which is normally referred to as the normalized EP, is quite high in comparison with the dense media based processes. Why do we want this EP value, or the normalized EP value, to be as small as possible? You can get a densimetric ore body where there's very little near density material, as shown on the graph on the left hand side. This small amount of material allows for a poorer efficiency without significant economic implications. However, when you are looking at high near density applications, this S-curve, or the EP value, needs to be as small as possible. And that's the territory where dense media, or fines DMS, can play a significant role. This graph illustrates that the dense media separation process is the most efficient process across a wide range of particle size. The particle size is shown on the x-axis, and the normalized EP is shown on the left-hand axis. So compared to water-only cyclones, WOC, MX7, which is the spirals, and then TBS, which is treated bed separators, the dense media cyclone. Next, we move on to some points to consider on fines dense media separation. First point, what size fraction do you as a client define as fines? Are we talking 3 mm to 0.1 mm? So 1.5 to 0.212 millimeters? That's the type of information we as suppliers need to be aware of. Does the separation improve if the fines fraction is treated separately from the rest of the ore body? If so, then there is merit for fines dense media separation. If not, maybe fines dense media separation is not the way to go. Dense media plants are expensive. If there's improvement in performance using only processing fines separately, does it justify the capex and opex that's required for this plant? What is the expected separation density that one is looking at? The amount of near density around the separation density, how much is that value? Is there a difference in the particle shape between the coarse and the fines material? Information that we as suppliers needs to know. Does the separation change if the media to ore ratio change? If you have that information, make the suppliers aware of that, because that is of utmost importance. And then how does the performance compare against other equipment, like the spiral, wet high intensity magnetic separator, or WIMS, TBS, theta bed separator, water only cyclones, reflux classifiers and flotation, and even shaking tables? If some of this equipment is producing results similar to the fines dense media separation process, maybe they are the better option from a capital perspective. Moving on then to challenges that we see so far in fines dense media separation. The desliming activity. Most of the plants currently is using normal vibrating screens or high frequency ultrafine screens. Screens or magnetic separators are used to separate the solids from the media. This is an area where one has to think very carefully, because the screen panel apertures are not always so small as the material that's been processed via the fines dense media process. Then magnetic separators is a possibility, but is the material magnetic, then magnetic separators is not going to do the job. What cyclone diameter do we need to use? That's one of the questions that's always been asked in the industry. The operating head. What operating head do we need to function at? Operating head is related to pressure, and pressure is a function of the media density. So in dense media alternatives, we talk about head instead of pressure. What media size and type will be required? What's the fineness of the media? That would be the best option. This is information that's not always available up front. How do we minimize the media losses from a fines dense media separation process? The separation density, is it the standard type of density or is it the ultra high density? Ultra high density is defined as densities above SG 3.8 or RD 3.8. Is the final moisture content relevant of the fine material? Viscosity, that depends on the type of media, and also the makeup water. If the makeup water contains some slimes, then that can result in viscosity problems, which can have a detrimental effect on fines dense media separation. How are we going to dewater the floats and sinks? What options exist to dewater that if we want to consider fines dense media separation? Next, I'm moving on to some flow sheets that has been developed over the years. The first fines dense media process flow sheet consisted of a normal dense media cyclone and the drain sections of each process reported back to the correct medium tank, and the rinse sections went separately to two separate magnetic separators. The magnetic separators recovered the media, and the effluent of the magnetic separators became then the fine product, with the discard section in this coal application moving to the discard side, and then the floats, which is a product in coal, producing then a 1/0 mm product. The results produced did not look too promising, although we could see that there was some separation taking place. If you look at the EPM values, remember the EPM values, the smaller the value, the better the separation efficiency. If we look at the finer fraction, 0.6 to 0.15 millimeters, the EPM values was relatively high. So that was not optimal, but it indicated some separation did take place. There was a modified wash to zero process, where the floats of a normal dense media cyclone went through the drain section of the drain and rinse screen into a separate tank and then get pumped to a second cyclone. This cyclone produced then a floats and a sinks. Both these streams went then through individual magnetic separators, and the floats magnetic separator effluent became the final product of the fines, and the effluent of the sinks magnetic separator became then the discard. This yielded an improvement in the EP values. As one can see that we went from 0.14 down to 0.1 on the fine fraction, 0.3 millimeter to 0.15 millimeters, and 0.75 millimeters to 0.3 millimeters, the EP became 0.05, which is actually quite good. The Fuel Research Institute of South Africa then went further, and they built a pilot plant where -1 millimeter was introduced to the process. It got deslimed via a hydrocyclone at 100 microns, and the -1 millimeter plus 100 microns was then fed into a dense media process. The cyclone's float and sink sections went then to individual 3-stage magnetic separators to produce then a product and a discard. The results indicated from the different test runs that very good EPM values could be achieved. Also take note of the magnetic losses experienced on this process. They are quite low, because the standard on magnetic losses in the coal industry ranges between 1.5 kg per ton to 0.5 kg per ton, depending on the coarseness of the material. So one would expect this fine material to be higher than 1.5, which is not. Multotec, a division of the CSIR here in South Africa, developed a different dense media plant. The difference is that it's still the same size fraction that was treated, -1 millimeter to +100 micron. But the difference came in that it was a 2-stage dense media process, where the float section of the primary dense media cyclone got rewashed through a secondary dense media cyclone, and thereby a discard and a product was again produced. The EPM values achieved on this process ranges from 0.05 to 0.065 EPM value, which is quite good. What's more significant is the organic efficiencies, ranging from 98 98.9 to 98.5, which is exceptional for fine cold DMS processes. One of the few industrial fines dense media plants is the Welgemeen plant here in South Africa, and this plant was also a two-stage dense media process. The products gets then dewatered through classifying cyclones and before discharge onto vibrating screens, and it can then discarded, or the product gets sent to the end customer. The results obtained on this plant also indicated EPM values of 0.019, which is very good. Organic efficiency 86.2%. So in this actual operation, the results that was obtained indicate that there is room, or there is a scope for fines dense media separation. It's not only on coal where fines dense media separation is used. Also on lithium, they use fines dense media separation. In this case, they split the feed between -6 mm to 1.4 mm and -1.4 mm to 0.3 mm. Separately treated then through a coarse and a fines DMS. Iron ore and andesite are also being used for fines dense media separation. So coal is not the only commodity that at this stage exploits the usage of fines dense media separation. Next topic is then the question about cyclone diameter. The Field Research Institute results was produced on a 240 mm cyclone. As you can see, EPM values was quite good. Over the years, different tests revealed that as the cyclone diameter becomes smaller, the EPM values becomes lower. So the trend is to use small diameter cyclones when you want to treat fine material, because that is where the best EPM values are being achieved. One can understand that if you look at this graph on the top left hand side. On a large diameter cyclone, there is a bypass of floats and even on sinks on the fine fraction, which is indicating that the large diameter cyclone, in this case an 800 mm unit, is not suitable for processing the fine material. Compare that then to a smaller diameter cyclone, one can see that these bypass fractions are being eliminated. Test work done between a 200 mm and a 360 mm cyclone do however indicate that we can maybe not go too small in cyclone diameter. The blue curve is illustrating the 200 mm cyclone, and as one can see, the larger cyclone produced a better EPM value. In diamonds, they're using 510 and 420 mm cyclones. But what is of importance is that on the 420 mm cyclone, there was cases where there was no 1 to 3 mm diamonds lost. Illustrating again, smaller diameter cyclone, better efficiency, if operated correctly. So, in summary on the cyclone diameter, this slide illustrates the various projects. The Multotec project used 360 mm and 250 mm cyclones. In Greenside, there was an operation using 150 mm cyclones. In Australia, the Cara mine, 500 mm cyclones. USA, 350, later 200 mm. We've got now 610 and 510 mm cyclones operating on two fines DMS industrial plants in South Africa. Andesite, smaller diameter cyclones again, 250 and 360. Australia, lithium, 360 and 250 mm cyclones. And then on fine iron ore, 250 and 360 mm seems to be the standard. The question is maybe what about 420 mm cyclones? So there's a range of cyclone diameters that is currently being employed or has been employed on fine dense media separation. It seems that there is no one size fits all. Moving on to cyclone pressure. What pressure do we need to operate, or operating head? The Field Research Institute results indicated that they were operating from heads between 54D to 9D. And if we follow these results, it seems that around 22D, shown by the cursor of the mouse, the lowest EP values was achieved. Additional test work done at Cara Mine in Australia also indicated a similar trend. 9D up to 24D test work was conducted, and the EP values seemed to improve as the operating head increased. On the Welgemeend coal plant, the industrial coal plant that's currently in operation, the feedback from site is, however, 9D, the standard operating head for dense media cyclones in coal, seems to be more beneficial than the 24D that people think is required on fines dense media separation. And the reason is that they believe that the cyclone starts to separate on size at these higher operating heads instead of density. They believe that the operating feed pressure should be between 9 to 12D. On lithium, 7D to 12D seems to be the standard. Andalusite, 12 to 20D, iron ore, 12D to 15D. So earlier test work indicated higher operating heads seem to produce better efficiencies, while as more data becomes available, it seems maybe lower pressures can be employed. Another factor on fines dense media separation is the media itself. The Fuel Research Institute developed their own size distribution on magnetite in the earlier years. On the graph on the left hand side, one can see what was the original magnetite, what was supplied to the process. They milled the magnetite and they reconstituted it to form their own type of size distribution, which is very similar to what was proposed by the Dutch state mines many years ago. Test work done at Homer City on 510mm cyclones indicated that as the magnetite became progressively finer, from coarse to fine to superfine, the EPM values started to improve as well. So a finer media seems to be the answer. On the Welgemeend coal plant, feedback is that the standard medium grade magnetite works well. So again, there's a contradiction. In some applications, finer media seems to produce better results, and then in other applications, the feedback is the media size distribution is acceptable. On ferrosilicon, you've got a range of media types. So therefore, one have the flexibility of changing the type of media between fine and coarse, and that makes it a bit easier. If one finds that one media is not operating correctly, one can switch over to another type of media. Another factor to keep in mind is that the overflow and underflow of the dense media cyclones on the fine processes, especially in coal, is going now through magnetic separators in most cases. And as the graphs on the right hand side illustrate, both for the product and for the discard, the finer media do get lost from the magnetic separator, and as the picture shows, it's getting lost because of entrainment. So keep that in mind. With fine dense media separation, if you go too fine in terms of media, it will or could progressively become coarse during the operation because of the losing of the media fraction. Next topic is that of the cut density versus the operating density. Your circulating media density shown on this graph here is ranging from just below 1.25 to 1.4. That's the circulating media density. And as you can see on the left hand side of this graph, your cut density is significantly higher. We start off at 1.55, just above 1.55, going up to a density of 2. So it's important to note that there's a big density shift between the operating density and the actual cut density on fine dense media separation. Now one can argue that you can just lower the operating density further if you want to reduce your cut density to even values below 1.55. As this graph illustrates, there's a catch. This graph illustrates that as the operating density was reduced from 2.72 to about 2.64, the cut density did come down. But if you reduce the operating density further, the cut density increases again. And that is because of the stability of the media. So there seems to be a limitation of how low we can go with cut densities on fine dense media separation. One of the problems, of course, is that we use smaller diameter cyclones in fine dense media separation, and therefore the classification effect on media is more significant compared to larger diameter cyclones. Next topic is the distribution. Because we are using smaller diameter cyclones, multiple cyclones are required to process a certain amount of tons. This is most of the times a single pump, which is then fed via a pulp distributor to multiple cyclones. But this design of the pulp distributor is of utmost importance. The picture on the left hand side shows a Y distributor with a bend before the Y distributor. The picture on the right hand side shows a standard 90-degree pulp distributor with the bend perpendicular to the outlets. In this pictures here, you can see the effect it has on the solids distribution. The Y distributor with the bend before it has progressively more solids on the one side. So more solids reporting to one outlet compared to the other. With the pulp distributor with a 90-degree outlet, there's a proper mixing taking place and distribution is quite even. So having a pulp distributor with the correct design, feed pipe design, is of utmost importance. There are plants that is utilizing this concept with multiple cyclones being fed then from a common distributor. However, on some of the fine dense media processes, people are feeding a single cyclone. That's where the larger diameter cyclone is coming in. There's no distribution problems that can possibly happen. It's a single feed going into the unit. So which one is better? The results done on a coal plant where multiple smaller diameter cyclones was replaced with a single diameter cyclone, it seems that going to a larger diameter cyclone resulted in improved EPM values. Test work done on lithium between two cyclones of 420 mm diameter compared to a single 610 diameter cyclone indicated that a single large diameter cyclone seems to produce better separation efficiency as well. So why would that be the case? Most possibly it's because of the distribution error that can occur using a pulp distributor when the feed pipe design is not optimal. We want as long or as straight as possible feed pipe into the pulp distributor with no bends, and if there are bends, it needs to be as far away from the pulp distributor as possible. But there does seem to be a trend that single cyclones, larger diameter, may provide better results in some cases. Next one is the particle size. What type of particle, what size range do we want to process with fine dense media separation? This graph indicated that there's a limitation. Ultra-fine material, dense media separation efficiency deteriorates as well. So it seems that at this stage the trend is that below 100 microns, that needs to go to a separate process. This also illustrated in these two graphs. Top left-hand graph illustrates the particle size and cut density. And the finer we go, the more significant the cut density effect appears to be. So there seems to be a cutoff where over a certain range we can separate the particles at a similar cut density, and on the finer fractions we are going to separate at a higher density. And that could be detrimental for the process. Moving on to the EP graph on the bottom right hand side. Fine EP values seems to be more consistent over a certain range up to the finer fraction, and then the EP values escalate. Illustrating again the argument to not process the ultrafine material. There's other processes that's more suitable. This was done for coal. Then there's a question of single versus double stage dense media separation. The Welgemeen plant, which is the operational plant here in South Africa, utilizes a two-stage dense media process. On lithium, the standard was using two-stage process, where you've got a rougher DMS treating 6 by 1 mm material, and then the tails went to a scavenger DMS, which will then reprocess some of the material. There seems to be now a trend that they want to separate the size fraction into a coarse and fines fraction, and then have single dense media cyclones instead of the original two-stage dense media cyclone. The question can be why? And I think one of the main answers is the difficulty of operation. Operating a two-stage dense media process is a bit more complicated than a single-stage dense media process. And if you don't get it right, it defeats the objective. Then single-stage DMS processes is more acceptable. Iron ore and andesite also utilizes only single-stage dense media process. So in conclusion, normally the cyclone diameter is small, but as you can see, there are some deviations. The media size distribution is important, but it also seems to be influenced by the cyclone diameter and operating head. Operating pressure, there's no certain standard at this point in time, but it seems that there are some industry guidelines, and that is what we as suppliers use at this point in time. But the media size distribution do play an important role. And if we as suppliers are aware of that, we may deviate from the industry standards. Narrow feed size range seems to be the optimum option for processing fines in dense media separation. That seems to provide the best results. And then test work. The more test work is done up front, the more accurate the answers will be. So the slide started off with the question, are we there yet? And the answer is not yet. We know a lot, but there still seem to be some factors that deviate from process to process, and there's more to learn. Thank you.